switch to the next presentation. And want to make start here.
Just hand it to the next guy.
Highlight response and dynamic
Thank you.
of aluminosilicate glass under compression loading.
So here.
Yeah. This one. Our respected chairman, honorable professors, and ladies and gentlemen, good morning. Thank you very much for giving us the opportunity to share our research work at this forum. I am Muhammad Zakir Sheikh from Pakistan, and I'm currently pursuing my PhD from Northwestern Polytechnical University, Xi'an, China. My PhD research topic is the study of wave propagation and impact damage in transparent materials. So as just one part of my research work, which is titled as High Rate Response and Dynamic Failure of Aluminosilicate Glass Under Compression Loading, I will discuss with you today. So the sequence of presentation is as follows. First, I will just brief about the glass and the aim of the study, and then followed by the experimental techniques which we have used during this research work. And then I will discuss some results, and finally I will conclude my presentation. So glass is one of the key component which is used as a vision element in aircrafts, high-speed trains, and combat vehicles. It's brittle. It's hard and brittle, and on the basis of composition, various types of glass exist. Namely the soda-lime glass, aluminosilicate glass, and borosilicate glass, etc. Today we will just discuss about the aluminosilicate glass. The compressive strength of glasses are very high as compared to their tensile strength, but they are very sensitive to micro cracks and flaws. There are various types of glass which are commercially available. Annealed glass, this is the first basic form of the flat glass which is produced in the process of float. This glass is very common, which is used in many applications. But the problem is that this glass, when breaks, it breaks into large big shards, which cause some safety problems. But this is the basic type of the glass which can be used to do some tempering process to get more quality glass. So through the tempering process we can we can get the fully tempered glass, toughened glass, or heat strengthened glass. The advantage is that the tempered glass, when it breaks during the impact, it breaks into small pieces which are less harm to the installations or to the persons. And another type is the laminated glass. The laminated glass is built by the combination of two or more glass layers with one or more layers of polymeric interlayer. So when under impact, when glass shatters into small fragments, so the interlayer can grasp that fragments too, and that's why it's used in many safety applications. The most modern form to make the glass tempering process is a chemically strengthened glass. In this method, the glass is submerged into the potassium salt, so that the sodium ions present on the glass surface are replaced with the potassium ions. Because the potassium ions are larger in size, so during the ion exchange process, the small gaps filled by the larger potassium ions, so the top surface of the chemically strengthened glass is in compression and the internal core is in tension. And the advantage of this process is that we can get very thin layer of up to 100 to 300 micrometer thin layer and up to the strength of 1 GPa. So because of this development of chemically strengthened glass, it's used in civil, military, and transport vehicle is increased. These are some of the applications where the glasses are used. In our research work, we have studied the static and dynamic compression behavior of strengthened and annealed glass experimentally by using mechanical characterization, and we have used universal testing machine and split Hopkinson pressure bar. On the right side, we can see a typical design of a front windscreen of the aircraft and a transparent armor. So actually, it's a combination of glass layers and a polymeric interlayer. So it's very important to choose the appropriate combination for an optimized design for the required application. So our current research work is focused toward the design of a front windscreen for the first Chinese civil aircraft that named C919. Maybe you heard about that. So coming towards the experimental part, we have cut, ground, and polished the cubic specimen of size 8 millimeter from the as-received glass plates, annealed and chemically strengthened aluminosilicate glass plates. The chemically strengthened glass plates which we have received, it has only the top and the bottom surface with the chemical layer of 115 micrometer, and its compressive strength is 600 MPa. The table shows the bulk properties, measured bulk properties of both types of glass. Firstly, we have conducted the static compression test in the strain rate range from 10 raised to the power -4 and -3 per second. And the setup is shown here. The stress or the load is measured through the built-in load cell with the machine. And in brittle materials like glass, it's very difficult to measure the strain accurately. So we have directly pasted the strain gauges on the specimen. And also we have used the high-speed camera to capture the failure process. So this is typically the force time and the strain time curve and the loading and the fracture process for the static loading. And the next part is the dynamic compression test, because most high-speed trains or aircrafts, when they are impacted, they are in situation of dynamic loading. So we have used the famous technology that are named as the Aluminosilicate bar or the modified split Hopkinson pressure bar. It consists of the projectile, incident bar, and the transmitted bar. Generally, the specimen is sandwiched between the incident and the transmitted bar. But in this case, because the glass compressive strength is very high, and to avoid the indentation effect, we have used the hard steel platens to protect the bar ends from plastic deformation. And to see the real-time deformation and damage process, we have used the ultra-high-speed camera with the framing rate of 1 million frames per second. And all the setup, the high-speed camera and the loading process is synchronized so that we can get the real-time deformation process with the synchronized strain histories to get the stress strain curves. Also, it's very important to have the appropriate incident pulse shaping to deform the specimen at constant loading. So we have pasted the copper and the combination of aluminum pulse shaper at the incident end. These are some results for the static compression test for both types of glass at 2 strain rates. We can see that its behavior is linear elastic and brittle till fracture. In annealed glass, there is some variation in peak strength of the pre-peak strength. This is because the annealed glass has some flaws which cause the variation in the compressive strength. However, due to the chemically strengthening process, the flaws are minimized, so there is less variation in chemically strengthened glass. Coming towards the dynamic compression test results. In dynamic compression test, it is very important to deform the specimen at uniform loading rate, and there should be stress equilibrium. So we have used, I already mentioned, a combination of appropriate pulse shaper. It's a combination of aluminum and copper discs. And this is the original oscilloscope record for the incident, reflected and transmitted wave. So basically this plateau region shows that the specimen is deformed uniformly before the failure. And also we have checked the dynamic equilibrium during the testing. There's a relation given by the Subhash et al. This parameter should be less than or equal to the 5% during the testing. So this is the plot for the stress and strain rate time, and also the dynamic equilibrium parameter. So this shows that the validation of our process, so that we can reliably give the stress strain curves for the glass materials. These are just the average peak compressive strength values for both types of glass. So in chemically strengthened glass, this value is somewhat 100 MPa higher than the annealed glass. These are the stress strain curves which we obtained for both the materials during the testing, dynamic compression testing. Another important effect is we have to see whether they are rate sensitive or not. So we have plotted the compressive strength values against the strain rates. So this result shows that the both glass are rate sensitive. And also we have collected the glass debris after the test. In annealed glass for the static compression test, because its tensile strength is very low, so it expands laterally, and finally it breaks into column, like in columnar failure. But in dynamic compression loading, when it's saturated with the cracks, and it fails into fine particles. However, in comparison to this, the chemically strengthened glass, for static compression and dynamic compression, both it fails into fine particles. Another important aspect is we have used the high-speed imagery to see the dynamic damage initiation and propagation in both materials. So the 9 numeral points on the stress time curves are synchronized with the high-speed images which we captured during the testing. So we can see that at 33.6 microsecond, the dark points appear. Because we have used the testing technique in the shadow graph mode. So initially, when there is no damage or the crack, it's bright. As some damage or the crack starts to appear, the region becomes dark. So the damage starts from here, it grows with time, and it gets the shape of hemispherical damage front. And then the cracks from the incident and the transmitted end grow towards each other and coalesce, and finally the specimen is ruptured. One very interesting phenomenon which we captured, the damage front is initiated, and after just 8 microseconds, it freezes and stays there during the whole deformation process. In a similar way, this is also the stress time curve with the associated high-speed images. So in this, we can see that in chemically strengthened glass, once the damage starts, it continues in an abrupt manner towards and leads towards the final failure. In comparison to annealed glass, there is no damage front is captured in this type of glass. So we have done the static compression test on 2 types of glass. We're using a universal testing machine and split Hopkinson pressure bar, and we have studied the damage process through the accompanied high-speed camera. Both types of glass show the rate sensitivity, and the average compressive or failure strength of the chemically strengthened glass is approximately 100 MPa higher than the annealed glass. And it's very challenging because the compressive strength of the glasses are very high as compared to their strain. So we were successfully obtained the strain time curves during the experiments for both static and dynamic, and we are able to get the stress strain curves. These curves will be useful to develop the constitutive relation for the simulation purpose. And the failure process in both types of glass is because of the axial cracks, and the axial microscopic cracks speed is 800 meters per second for the annealed glass and 1000 meters per second for the chemically strengthened glass. As a future work, because we have studied just the compression part, so to study its tensile behavior is in progress. So far we have conducted the static tensile test. This is based on the famous Brazilian test. The concept is that the 2 surfaces in contact with the fixed bar and the moving bar are in compression, but the internal is tension. So when the damage starts from the center, it breaks into split into two parts. It's very important that damage should start from the center to get the appropriate results. If it breaks from the loading ends, the test is not accurate. I have presented here one of the test videos captured during the test to see the tensile behavior. It splits into clearly two parts. So thank you for your attention.